So remember, the first thing I mentioned was quantum computers work as a hybrid with classical ones for solving hard problems. The second thing I wanted you to remember is PennyLane.ai. So PennyLane is also a Beatles song. If you just Google PennyLane, you'll probably get a Beatles song. So if you Google PennyLane Quantum or PennyLane AI, you will find the right PennyLane. And PennyLane, I mentioned it's a Python library for programming quantum computers, but it's more than that, right? It's a community. I am quantum community manager at Xanadu. I help build the community. So we're not only a bunch of code in a GitHub repo, we're a lot of people who are solving applications, who are exploring new things, who are learning. So we have a lot of education resources. We have a lot of papers that we implement. We have events, talks, etc. We want PennyLane to be the place to go for quantum computing. And so PennyLane is more than a GitHub repo or an amazing documentation, which you will never find such a good documentation. We're very proud of it. And here you can see some of the partners. Also, something really good is that the goal of PennyLane is that you can program once and then run everywhere. So you don't need to create several versions of your code to run it on different kinds of quantum hardware or to interface it with the different maybe libraries that you're used to using. PennyLane is built to integrate or to run on different kinds of hardware. So it's hardware and framework agnostic. And this is, yeah. Below you can see QHack, which is our main event of the year. I'll mention that at the end too. You will also see that PennyLane is built for differentiable programming of quantum computers. So differentiability is at the core of PennyLane. It's how it was built, because we know how important it is for machine learning, and we expect that it will be very important to train quantum computers. We want people to be able to train them in an efficient way, and so we've built differentiability at the core of PennyLane. Is there a question? I see something.
Just answering questions about Jupyter in the background.
Okay.
Don't worry.
All right. So, any questions about PennyLane so far? Okay. So, oh, I see something. Not so far. Okay, good. PennyLane uses a very smart way of helping you build your circuits. So the first thing that you're going to see is that you're going to see Qnodes. This is kind of our signature. Wherever you see Qnodes, you're going to see that there's PennyLane underneath. PennyLane uses these Qnodes to encompass everything that is quantum. So you can have TensorFlow, PyTorch, etc. running, and then you can have, and then let me go back one slide. You can have modular hybrid algorithms. So if you see the picture on the right, the orange ones represent classical modules, and then the green ones represent quantum ones. So when we built PennyLane, we created these Qnodes where everything that is quantum is contained inside. And so you can have some classical inputs and some classical output, and you can program that quantum part that is inside, which is a Qnode. So it's just a special Python function. Quantum circuits, this is how they look. So how do you read a quantum circuit? First, you're going to see these zeros at the beginning. They're often zeros, but they could actually be zeros or ones. They're your initial state. They could sometimes be represented as psi or some other number. So usually you will always start with an initial state that is 0. So your qubits, which are this unit of computation, will have an initial starting point. Because it's 0, you can then add things to it. So you see 1 0, 2 zeros, and 3 zeros. The first one represents the first qubit. So you can have circuits that use multiple qubits. Here we have a 3-qubit circuit because you see 3 large horizontal lines. So each of these horizontal lines represents a qubit. In PennyLane, we call them wires. They kind of look like wires. If you really look at it, they look like these long wires. So you start with each qubit in state 0. You distinguish it from a classical state by using this notation of a vertical bar and then this kind of triangular bracket. This is called the Dirac notation. And so these represent your initial states. You have these horizontal lines, which are your qubits, and you have these things in the middle, these squares and these circles, these weird circles, those are your gates. So the first one here is a C0, a controlled NOT gate. What this will do is it will negate whatever the second qubit is, the value of the second qubit, if the first qubit is a 1. In this case, you start with 0 and you move in time from left to right. So that is like time steps, you can think of it. So in the first time set, we have 2 gates. We have one where if qubit number 1 is 1, it will negate the second one. So in this case, both are 0, they will stay as 0. The other gate happening at the same time step is this Rx gate. This is a rotation gate, which takes a parameter theta. So what it will do is it will modify my quantum state. So it starts in 0. And you can imagine it's like having an arrow pointing somewhere inside a unit sphere. So inside a sphere, and you're changing the state, it's modifying where that arrow is pointing. And it is parameterized. It's a parameterized gate because it takes a parameter theta. Now you have another gate here called H. This is a special gate called Hadamard. So this is the gate that will create what is called quantum superposition. And this does not mean that something will be in 0 and 1 at the same time. It's actually a linear combination of 2 quantum states. But it's not both at the same time. It's something else. It's something else. So you can imagine having a coin. A classical coin it can be heads or tails. And having a quantum coin, it's like having it rotating in the air. So that would be like a qubit. It's not heads or tails. It's like a linear combination of both. And you have a certain probability of your coin landing on heads and a certain probability of it landing on tails. But it's not both at the same time. It's kind of something else. So mathematically, it's a linear combination of the 2 basis states that you use, which in general just 0 and 1, or it could be different states. All right, so really what matters is to know that this is a gate that will modify, the state of your qubit. So you can imagine it's all of these gates, it's like getting your coin and modifying the rotation, how it's rotating in the air. It will modify the way it's behaving, and it will modify the probabilities of having that coin landing on heads or on tails. Those other gates, you can have these, so this one that has like this circle with like this plus and these 2 dots. This is a controlled NOT. So the the full dots, the full black dots are the control, and this like kind of X thing here, like this plus with the circle, that is the target. So here, if the last two qubits are 1, then the first qubit will change its value. And for the last one, you have another controlled gate, but in this case, what it means is that if the first qubit is 1, then you should apply this RY gate. That's what it means. And again, it takes a parameter. And finally, at the end, you have measurement. This is very important because going back to the coin analogy, if you have your coin rotating in the air, you won't really know anything about it. So you need to measure it. You need to grab it, let it drop, and you will get a classical output, a classical measurement. You can imagine this as collapsing to a 0 or a 1. But the way you run these experiments many times and you get some statistics about them, and then you can interpret your results. There are some algorithms where you just need to run once, but most of the time you will need to run many times. This is what is called shots. So this is, I know for the people who are beginners in quantum computing, this will feel confusing. So please ask your questions. This is the right moment for that. All right. If you don't have questions, I'll have to ask them. So how many time steps would it take for the circuit to run the circuit? Oh, here I see a question. What determines the probability after the H gate? Good question. So the H gate is very particular. It allows us to go from a 0 state to an equal superposition of 0 and 1. So it's like the middle step between 0 and 1. And then if you start in 1, it again will give point you to like the middle step between 0 and 1. And if you start in the middle, it will take you either to 0 or to 1, depending on where you are, something like this. So what determines the probabilities after the H gate? It will depend on everything that is around it. So if you had nothing, so in this case, say you start with 0, this is 0, and you apply a Hadamard gate, then just after the H gate, if you measured right here, right after the H gate, you would get 50% chance of getting a 0 and 50% chance of getting a 1. That is if you measure it right after it. But if you do other things, then your probabilities will change, right? If I added another Hadamard right after this first one, then they would cancel each other out. And then I would get whatever was before them. So that's a good question. Is there a sandbox to play with qubits online? Yes, absolutely. So that was actually the goal for today, was to show you how to do that. I'll have to make a shortened version of it, but I'll show you how you can play. First of all, most of the times we use simulators. So we run on classical computers that simulate the behavior of quantum computers. But they are very useful for us to learn and develop quantum algorithms. So there's a whole new math that we need to develop and whole new algorithms that we need to develop in order to solve our problems. So what in general is recommended to do is that if you have a problem, try to figure out what is the smallest version possible of your problem and try to run it on a simulator that can help you understand how you would solve this problem. And then if there is a quantum computer that is available that you can use and etc., then you might try to run it there, but only after you have tested all of your hypotheses and your algorithms on a simulator. That is the general best practice, because using an actual quantum computer is expensive. It's sometimes you'll have to wait a long time in the queue, or it will just be unavailable, or they may be very noisy and they won't give you any reasonable answer. So all of the all of these that I've mentioned are why you generally start with a simulator. And having GPUs, having access to high performance classical computing is a very good way to test, larger test cases, but still something that we can run on a classical computer. Now, if you want to simulate hundreds of qubits, this is something that we cannot do today on classical computers, but we're getting better and better at it. So I hope that in a few years, maybe we can, or maybe less, I don't know. Depending on what your circuit is doing, you can already do that. So there, actually our company simulated a 100 qubit computer, I think it was last year, using a specific tool that we have. How many qubits does Setonix support? How many qubits depends on your RAM, the RAM that you have available. So usually for the 40 to 80 gigas of RAM on a GPU, you would get to run about 29 to 30 qubits. But again, there are tools that you can use that can help you improve that number. And there are things you can do to improve your circuits that can help you improve that number again. So it's not an easy question. It will depend on what you're doing. For example, if you're working with mixed simulators with noise, that number goes down drastically. If you're working with noise, then just the math, the matrices that you need to put into your system are just very, very large. And so that number will go down. But normally, to give you like a sense, for a circuit that is not too deep or like moderately deep, you could run 29 qubits on about 40 to 80 gigas of RAM. The PennyLane circularity coordinator is a simulator. Or, I'm sorry. A PennyLane is the library, and the library contains simulators. Oh, I see Pascal saying if you use all of the GPU nodes, yeah, well, it depends on how many GPU nodes you have. You might be able to simulate more. Although 45 sounds like something huge, but yeah, possibly. Possibly. The PennyLane circular container is so again, PennyLane has like built-in simulators. So the container is not the simulator. The simulator is, say, PennyLane Lightning is a simulator, or default qubit would be a simulator, or we have a default AWS that would be a simulator. So the container is just a container, and the simulator would be something else. Good questions. Oh, what's the difference between running on a simulator and an actual quantum computer? Very good question. On an actual quantum computer, you would potentially be able to solve things that you cannot solve on a classical computer, right? So that's the point of building quantum computers. It's because each qubit can encode so much more information. You can encode a lot more information in each qubit, and you can create those circuits. It's not only that, it's really the fact that you can create entanglement. You can create something called entanglement between qubits, which you can think of it like creating a certain correlation between those qubits. Then the power of computation, of like running these computations, becomes exponentially difficult. So running a quantum circuit with 28 qubits is twice as easy as with 29. So running 29 qubits requires twice as many resources as running 28, and so on. So there's a point where it just becomes impossible to simulate some circuits with a classical computer. So that is when you would need a quantum computer to solve certain problems. For example, if you want to simulate just one molecule of coffee, it's impossible. It's mathematically impossible to solve it in any classical computer if you want to get to a certain level of detail. Of course, if you just look at it on the very high level, you can get an approximation. But to understand it to a very, very high level of detail, it just becomes impossible. So that's the interest of having quantum computers. And at some point, having simulators, I mean, for now, it's the best option. For now, it's the best option, and it can help us solve problems that maybe would be impossible to solve without these simulators. Maybe it can help us, bridge the gap between now and when the quantum computers get better too. And it can also help us improve our classical, workflows. So by working together with these simulators and your normal classical workflows, you might be able to find some advantages. So yeah, but they are definitely different. It's very different to run on a simulator and on an actual quantum computer, because the simulator is running on a classical computer. Okay, I think all of the questions have been answered, but great questions. And if you do have any more, keep them coming. So something that makes it very interesting as well to run quantum algorithms is running something called variational quantum circuits. So variational quantum circuits are basically how the following flow. You start with something called an ansatz, which is a specific set of gates, where you start with usually any parameters. You just choose some that you hope are going to fall near to the minimum, or maybe not near a flat space in your cost function. So you start with some layout, which is called the ansatz. That's like the circuit layout with the gates. Often in PennyLane and in general, you are going to want to use expectation values. So you're gonna see that in a lot of the tutorials that people use expectation values, and this is basically a function of your gates and your parameters. And here we make a distinction between x, which is fixed data, and theta, which is our variational parameters, which we will vary after every iteration. Then we can build cost functions. Similarly to how you would do it in a classical computer, you can combine different Qnodes, or you can add classical parts to your cost functions as well. And then you can join them into a specific training procedure. So you can choose an optimizer, you can use gradient descent, you can use Adam, you can use others. And then you can keep updating those parameters theta. So that is like the main workflow of how a variational quantum circuit works. And this is a very popular one. It's not the only one. There are many people who don't use variational quantum circuits, but that is, I'm going to say, like what most people probably use today are variational circuits. Maybe just one last important thing is all of my gates. So everything that happens until right before the measurement is basically just vector matrix multiplication, because my states, my input states, we start with vectors. These are vectors. My gates can be represented as matrices, and the way you know the state after a certain gate is it's a vector matrix multiplication all the way until the measurement. That is a non-reversible part of the computation, and that is where the linear algebra breaks. But everything else, everything that happens before, it's just linear algebra. So very useful. Oh, I see there's another question. For circuits that have been tested successful in PennyLane, is it guaranteed to run on a quantum computer? There are some things, so PennyLane is a library for hybrid workflows. So there are some things that are built specifically for simulators. And for example, you will see there is something called adjoint differentiation, which is really cool. It can allow you to differentiate circuits and do training much faster, but it only works on simulators, right? But we know that like it's built with that in mind. It's built to help you speed up, your computations on simulators. If you don't need that, then we also have differentiation techniques. And actually, this is a differentiator of PennyLane. We have differentiation that is specifically for quantum hardware. So it's a little bit slower. This is why we don't generally use it when we're in simulation. But it's called parameter shift. The parameter shift rule is something that can help you do differentiation on actual quantum hardware. And many of the things, probably most, that you can do on simulation, maybe not most, but many of the things that you do on simulation, you also do on quantum hardware, but it's important. So the question is very good. It's important to know what can run on hardware and what can run on simulators. If you want to output, for example, the state vector of a circuit, this is not something that can run on hardware because this is physically impossible. Like you cannot get it. Or for example, you cannot do backpropagation. You cannot do backpropagation on hardware. You can, however, use the parameter shift rule, and PennyLane will put it as a black box in the middle of your machine learning workflows. If you have something on PyTorch and you want to use backprop, it will basically interface with PennyLane, ask what is the gradient. We will calculate it using whatever is the best method, depending on what your device is. If it's a hardware device or a simulator device, we will know that. And then we will get PyTorch, the answer. This is the gradient. And PyTorch doesn't have to know what happened in the middle. So there are some, just to summarize, yes, some things only run on simulators, and you need to be careful about what is not compatible with hardware. All right, so I mentioned this, we're framework and hardware agnostic, but just to give you an idea, there are so many different hardware technologies. So neutral atoms, trapped ions, superconducting qubits, photonics, and simulators of all kinds. My recommendation would be generally, if you want to run something specifically on hardware, you can start with superconducting qubits. It's generally easy. So you could start with something that you can run on IBM or on AWS Bracket. Yeah, I generally only recommended photonics if this is your area of expertise. If you're specifically like an expert in optics and photonics, then you can start there. But generally, usually, it's if you want to run on hardware, it's easier to start somewhere else. Now, in the future, of course, when we get those fault-tolerant modules, PennyLane is the tool to use that, right? So it will become easier, but we're still building the hardware, so we'll have to wait a little bit more for that. And these are some of the devices that are available. Lightning Qubit is my personal favorite. It runs on a CPU, so it's based on C++, easy to use, very fast. And Lightning GPU works on NVIDIA simulators, so you can run on Setonix using Lightning GPU. If you had access to Lightning Cocos, if you wanted to run something on Lightning Cocos, you could also do that.